Now let's solve the second problem of today. This structure is attached to the bottom of the surface, and as you can see, the dimension is really complex. Like there is 140 and 40 millimeter, 20 millimeter, 70 millimeter, 100 millimeter, 200 millimeter, and 130 millimeter. Actually, you're gonna need all of those informations, 25 millimeter. This problem asks us this question. First, the problem asks us determine the reaction at EFG plane. EFG plane is EFG plane. This is the plane where the point H is located. And the second question asks us obtain the normal stress and shear stress at H. Yeah, this H point is the infinitesimal volume, where which is located at the surface, and 25 millimeter located from the center of z equals 0 position. Okay, so at this infinitesimal volume, we have to obtain normal stress and shear stress. And then as a third question, based on normal stress and shear stress, we have to obtain principal shear stress and maximum shear stress at H. Okay, so yeah, this is what you can see here is, this problem combines everything. So what you can expect about EFG plane is we're gonna have normal force and vertical force and moment, and we have everything except torsion. Okay, so let's see how we can solve this. Let's start from the first problem. So let's look at the first problem. So this is the full free body diagram, and after we take out the volume above this EFG plane, then we can draw the free body diagram like this. So we have to draw reactions N, B, T, and everything at the centroid position. So what you have to do first is you have to move the forces first. So 50 kilonewton in y direction, it will be counted as 50 kilonewton n equal 50 kilonewton. Then we have this shearing force 75 kilonewton. It is along negative g direction, so we have Vg. And we have 30 kilonewton, which is along the x direction. We have 30 kilonewton like this. Now, even though we move these forces to the centroid position, we cannot account all the reactions from these three forces. Actually, this guy induces a moment about x-axis. This guy also induced moment about x-axis. This guy induced moment about z-axis. So we have to obtain mx and mg. So suppose that actually in principle, if we consider right hand rule, the mx should not be in this way, but somehow our problem, the free body diagram in our textbook considers this direction as positive m direction. So I just try to get aligned with the definition of our textbook. So according to our textbook definition, this is mx. So the mx vector in that direction, 75 kilonewton multiplied by 200 is positive sign. Mx direction defined in that direction, 50 kilonewton multiplied by 130 millimeter is negative sign. So if you do 75 times 200 and do minus 50 multiplied by 130, it gives us 8.5 kilonewton meter. Then about the mg, where's mg? This guy gives us mg. What we have to do is we have to multiply 30 kilonewton with the position 100 millimeter. So after multiplying these two, we're gonna obtain 3 kilonewton meter. So after obtaining normal stress, shear stress, and moment, we can complete the reaction diagram at the EFG surface. Then after obtaining EFG reactions, we have to also get the section property. You will need area, simply multiplying the dimension here and here. So we need also I in two directions, about x and about g. So about x and g, you simply apply that into 1/12 bh cube equation, and this is what you're gonna get. So you can see that ix is much larger than ig, because ix with respect to x-axis, we have large volume quite far from this x. But however, when you consider ig, which is the about this g-axis, you have volumes quite near to the axis, so that you have a much similar IG, which is less than like a 10% of IX. Okay, even though the cross-sectional area is the same, depending on your rotation axis, your I value can be very different. Now, having obtained the reactions and the section geometrical property, it's time to obtain the normal stress and shear stress at H point. So H point is located here. Okay, and from the it's really small. From the z-axis, this is 25 millimeter, and it's located at the surface. So at this point, let's take a top view. So E is here, and F is here, and G is there. So, and our famous H is here, which is 25 millimeter or 0.025 meter from the center. 25 millimeter. So given this, to obtain sigma y is the normal stress out of this EFG plane. So we have three reactions that affect sigma y, which is normal force and 50 kilonewton, and you have to divide n with a. Now after that, you need mg. So mg also give rise to what you can see like here, due to this direction. When g is negative number, when g is g has a negative sign, it must be tension. Okay, so our mg is 3 kilonewton. So you have x times mg times ig. I made a mistake. Due to mg, you have the normal force, normal stress as a function of x. Okay, as a function of x position, and when x is positive, the sigma g must be positive. So you have to get your sign correctly. So when x is positive, because mg is given as positive number, according to our sign, according to our sign of a textbook, you have to take x and mg over ix, such that when x is positive number, you have positive contribution of our sigma y. Now let's move on to mx. We take mx, this as positive sign. So what you can expect here is, due to this mx, when g is negative number, you out of this mx, you expect compressive force. So when g is negative sign, the sigma y due to mx must be negative number. So h has this is positive direction of g, and h is located like a negative 0.025 millimeter. So if you simply plug in mx over ix multiplied z, because h is located at g is less than 0 position, so you can correctly say this is a compressive sign or negative sign. So I don't know why our textbook has this kind of sign definition. If you define your sign according to the right hand definition, taking positive axis as positive mx, you're gonna just simply use the equation we derived in previous chapter on the combined normal and moment loading. But somehow we anyway decide to follow the definition of our textbook solution. So this is how I follow the textbook definition of mx and mg, and why I put plus g and plus x here. Okay, so please make sure that this sign is consistent with your intuition. If you don't get mg and mx correctly according to the right hand rule, so after defining this, what you do is you simply plug in all the values. We have value of ix and iz and a, and we have value of n and mg and mx, and the at h point, the h point has g equal negative 0.025 meter, and about the x, x is 20 millimeter, 0.02 meter for value of x at h. Okay, so yeah, you plug in these two values here and there, and simply evaluate this equation. After doing all this calculation, it turns out to be 66.0 megapascal, which is tension along the y direction. Okay, so that's normal stress at H point. Now let's move on to the shear stress. So about shear force, we have like this is shear force and that's shear force. However, the shear force due to Vx, because H is located at the surface, the shear force along the x direction will be 0. However, if you consider shear force along g direction, what you can see here is along the g direction, even though the side wall is free surface, you can have finite value of shear stress along the g direction. Okay, so along the g direction, where we have Vg equals 75 kilonewton, what you do is at H point you do a Vq over It equation. So to apply Vq over It, the V is 75 kilonewton and Q is you do integral for that volume, and to do that you need to obtain A of that guy, which is 0.045 and multiplied by 0.04, and the location to the centroid of this guy is given as 0.0475 meter. Okay, so then you multiply 0.0457 meter, which gonna give us the value for Q. Then about the I, we have value about Ix from the previous page, and about the T, we have T of 0.04. So after plugging in all those numbers, the tau becomes 17.52 megapascal. I know that of course it's not easy to follow all those little tiny values step by step in this short video, so I highly recommend you to do this calculation by yourself. Just to if you just listen to my lecture and forget about it, you're not gonna learn. Please do solve this problem by yourself, and then please try to solve homework problems in chapter A by yourself, such that you become familiar with handling multiple reactions, multiple shear force, multiple normal force, and multiple moment and multiple torsion in some problems. Then combining everything to obtain in-plane Mohr circle and 3D Mohr circle, then you can obtain the answer appropriately. Okay, so anyway, the value for shear stress is 17.52 megapascal, and the component is YZ component. Now forget about XYZ component. The problem asks simply obtain the principal stress and maximum shearing stress at H point. Okay, so at H point, we have tau YG, but we don't have tau xy because it's on the surface. So if you take out this little tiny volume here, let's take out this cube at H point, then you have shearing stress 17.52 megapascal and y direction tension 66 megapascal. So if you define x tilde and y tilde coordinate system, and it becomes a simple Mohr circle problem in plane. So sigma x is 0, sigma y is 66, and tau xy is 17.52 megapascal. Then the average stress is simply this guy divided by 2. So you have 33. So if you plug in 33 and 66 and 17.52 to the equation for R, you obtained 37.4 megapascal. Then you take x and y position as value of sigma x, sigma y, and tau xy, which gonna give us these points 0 and negative 17.52 and 66 17.52. So this is x point, 0 and 17.52, and this is tau and this is sigma. Y is 66 and 17.52, and after completing the Mohr circle using this point, that point, and that point, and realizing that R is 37.4, so what you can expect is the two principal stress, max and mean, is 33 plus 73.4, which is R, and 33 sigma average minus 37.4, which is R, it gives us minus 7.4. Oh, is it true? No, it should be 4.4. Okay, and the maximum shearing stress must be 37.4 megapascal. Okay, so with this, starting from very complex geometry and very complex combination of reactions, we finally arrive at sigma max, sigma mean, and tau max value at each point. Okay, so with this, let me finish recording for the second example problem.